bracket cos P/2. And then on the other side is equal to 2e sine squared P/2. Okay. So we could get rid of the sine. Wrong color, I do apologize. We could get rid of the sine. You have a square down here. We come out with 2a cos P/2. And over here, we have 2e sine okay. So finally, we know that A will be equal to 2e sine P/2. And then we divide by the whole thing, 2 cos P/2. So finally, straightforward, A is equal to E tangent bracket P/2. So therefore, we found our A and B. The unique solution okay. The unique solution is y as a function of x. This will be equal to E tangent, right? P/2. And then we have sine px. And then we have plus E cos px. And then finally, we have minus E. Okay. So we gather the term together. E tangent P/2 sine px plus by cos px, okay, because we factor out the 2, and then minus 1. I think this is our equation number 9. Okay. Now there's one more condition that we know. Okay. So we know we're going to apply boundary condition number 3. It has to satisfy this boundary condition, as in when x is equal to L/2, y is equal to y max. Okay. So we are going to substitute this equation inside, okay, right, into equation number 9. So we know that we have y max will be equal to E, right? And then we have tangent bracket P/2. And then we have sine. Now x is also equal to what? P/2 plus by cos, right? PL bracket P/2. And the whole thing over here, we do a minus 1. Going to write this out in a different form. We know that this is sine P/2 and divide by cos P/2. And then we multiply by sine P/2. plus by cos P(L)/2 minus 1. So we have E. Now we have in the form sine squared P(L)/2 over cos P(L)/2. And then we have a plus cos P(L)/2. And then we have a what? We have a minus 1. Okay. So we are going to make a common denominator, E. Again, I think I need big brackets. Sine squared P(L)/2 plus by cos squared P(L)/2. And then over here, divide by cos P(L)/2. And the whole thing minus by 1. So this comes out with an expression, sine squared P(L)/2 plus by cos squared P(L)/2 is 1 over cos P(L)/2, and the whole thing minus 1. So therefore, the outcome of this is Y max is equal to E secant P(L)/2 minus by 1. Okay. And this is our equation 9a. And thank God, during Euler's time, there were no television. Now, no way, man. You do your homework for 10 minutes, 20 minutes, look at YouTube, the shorts, okay? Okay? I love Donald Trump. He's crazy, man, that guy. He's a nutter, man. It's good for stock market, okay? So note, right? Small p is equal to what? Square root PL. Also, P over what? EI. So now we are going to put things back, okay? Like what Donald Trump said, he's going to make it right. So we have Y max is equal to E. I'm going to put back the cosine, okay? So we have 1 over cos, right? So I'm going to put back square root P over EI. Okay. And then we still have the L/2 term. And then that we have a minus 1. So I think I put this in correctly. Okay. So now we are going to have conditions. Okay, we're going to have conditions. Not a boundary condition. But a condition that is true is that note Y max will tend towards infinity when what? Cos pi over 2, which is equal to 0. Okay, so I want you all to put your attention now into this term over here. and into here now. Okay. So 1 divided by 0, you cannot. It tends to what? Infinity. So when that's the case, we can write up the expression square root P over EI. Okay. Multiply by L over 2. And this is equal to pi over 2. Okay. We can get rid of the 2. We can write out P over EI is equal to pi squared over L squared. And then we can come up with an expression where P is equal to pi squared EI over L squared. This is also equal to PCR. Or we can have the expression which is EI, which is equal to what? EI is equal to critical stress multiplied by L squared. Okay, L squared over pi squared. Now, what you observe over here, this equation, have you seen it before? The answer is yes. So the critical load for centric and eccentric loading are the same. Can you see that? Right? Derived mathematically. It's not a hypothesis. Okay? It's derived mathematically. I'll see you guys tomorrow.